So one of the big wins in deep learning is the idea of transfer learning. This is a pretty simple concept that we can examine starting from CNNs. Recall that in a convolutional neural network, when we layer the architecture between having convolutions activation functions and pooling, we can get layers that are successively generalizing across features. So at the lower layers of the network, we're learning simple features such as intensities, edges, and textures. But as we move towards the middle layer and the output layers, we're starting to learn more complicated, complex features that are compound. For example, geometric shapes, or legs, or vehicle parts. And at the output level, something that is quite task-specific. For example, here we have pictures of dogs and other types of animals that we might want to see. So if we want to carry out a new image recognition task, probably the output layer is not going to be very helpful. But at least the middle layer and the lower layers especially have features that are pretty general. They're things that could be used in different types of feature detection. So for example, on ImageNet we have natural images, but let's say in the e-commerce data set we have products such as electronics, cosmetics, and clothes. Many of these features that are extracted at the middle layers and at the bottom layers could still be used to help that process. So this is in a nutshell the idea of transfer learning. We take a pre-trained network, for example one that's been trained on the very large image recognition challenge, and take parts of the network that have already been trained, for example the unsupervised feature extraction layers, the bottom and middle layers, and use them for a new task. And how do we do that? It's actually fairly simple. What we're going to do is we're going to either remove or re-initialize the task-specific final layers. For example, if we take the VGG network that we saw in the earlier part, we can take the last 4 layers consisting of the fully connected layers and the softmax, re-initialize them with random integers, and then train for a new data set. So we're going to, again, propagate forward through the network, get a detection result, and backprop, and tune all of the parameters. Specifically, we'd be targeting the parameters that are found in the new part of the network, which we have randomly initialized. In doing transfer learning, we have to think about the relation of the 2 data sets to each other. For example, if the task that I have pre-trained on, meaning the source network, which is already well-trained, is very large, and the new task that we're trying to target, it doesn't have a lot of data, we might want to freeze the body of the network, meaning that the weights for this part of the network we're just going to keep as is. We're not going to change them at all, okay? And then what we're doing is just training the top part of the network over here such that we could get good results on that. If we have a new task, the target task has a sufficient data set, for example, again, the e-commerce data set where there are lots of images on the web that have things related to online shopping, then we could retrain our entire network. But we would use the network weights that come from the previously trained network as initialization, and then continue training to refine the parameters so that they're optimum for the entire network. Interestingly, when we take the same task that we've trained a network already for, let's say it's well-tuned, and we lop off the final layers and we try to relearn the final layers from scratch, we find that it actually yields poor performance. And this is because the penultimate layers here are starting to co-adapt features that are actually specific for the network that it was actually fully trained on. But when we lop off these layers and we take new weights for them, then these layers here that we've outlined don't work quite as well. They've already sort of adapted to the fact that there's these parts that are already present. This is why in transfer learning, it's a hyperparameter to decide where in the network to cut off and re-initialize. We could just cut off at the softmax, cut off somewhere in the fully connected layers, or cut off maybe even at certain blocks of the pooling layers. Each time we cut off at a different level, we're using less and less of the automatically extracted features that have been achieved by the neural network on the previous source task. and asking the network to learn new features, new compound features, and new output features that are for the target task. So when is it a good time to use transfer learning? Well, it's important to consider this fact that the two tasks have to have the same type of input. For example, you have to be using images to transfer to an image task. But they also have to be somewhat similar. For example, if you're looking at black and white radiology pictures, probably transferring from VGGNet wouldn't be very helpful because it has already learned color features as well as features for natural images that are not part of the domain of radiology images. Transfer learning is also very helpful when the source data set, the task A, has a lot of data, and when we don't have sufficient data to learn the parameters of our network well for a new task. In these cases, we can use the network settings that have already been established on the larger source task as a source of stability and to fine-tune those parameters when we're looking at the target task B. Finally, it can be very helpful when the features extracted from the source task A can be helpfully applied for task B, and we've already alluded to that on the previous slide. In fact, we've seen transfer learning a little bit already. It comes under a different name of doing embeddings. So the idea of an embedding is actually a form of transfer learning. It's the idea to take the input and put it into a format that are going to be more semantically meaningful. What we want to do is take the raw inputs that we have, either words, images, etc., and try to represent them in a way that's helpful for learning. So this is called representation learning. And we already saw how to do this in the previous pre-lecture by using this auto-encoding idea. We're basically asking a separate neural network to take the inputs of a certain dimensionality and recover it exactly as is with the same dimensionality on the output, but using much less features that we can encode. So squeezing all of the semantic representation into this smaller network and then discarding this part as output and using this as a representation. So we can think of this as an embedding. Okay? And these embeddings often can have additional soft constraints that we add into the cost function. For example, when we create word embeddings for natural language processing, we want to enforce the idea that similar words like nurse and doctor should share similar context in the texts that they occur in. A big win in deep neural networks is to do machine translation like Google Translate. For this reason, we can think of multilingual word embeddings as having an additional constraint. Word-to-word translations should be near each other. So if I have the Japanese word kuruma, the Chinese word ce, the English word car, and the Spanish word carro, they should be all placed quite close to each other in the multilingual embedding. We can even extend this even to modalities that are not close to each other. In fact, scientists have found that when we take images and their captions that we find on the web, we can embed the images and words in the same semantic space as represented by an embedding, and that they can be located near each other to recover a mapping between words and their images.